Hello. Yeah, I'm sure I'm audible. We'll start in a few minutes. Okay. I will begin. So, for those of you who are joining new, my name is Harish, and I'm a PhD scholar at IIT Hyderabad. And for those of you who are used to joining, um, you know the usual strategy of these live sessions and classes, right? So the fundamental idea is for us to supplement the material in the original or in the main course that you're looking at. We supplement that with extra knowledge, and the main way by which we want to supplement that is by solving questions. So we take the previous year questions and we explain the questions and we try and solve it in front of you, right? Before we do that, we also provide some context on what is what was taught in this week and what it is that we are expected to understand from this set of classes that you took. And as always, the classes are recorded, so you can take a look at the recorded classes. So there is no compulsion that you'll have to join, but if you want to ask questions, you can ask questions when you're joining. And this is expected to be more of a discussion based session, but so you're free to stop me at any point of time, ask questions. If I know the answer, I'll let you know. If I don't know the answer, I'll find the answer and let you know. Right. And there are two such sessions that happen. One session that happens is on Fridays, and the other one is on Tuesdays. Right. Okay, so since past 2 or 3 weeks, I've been following one particular pattern. Pattern is we first read through all the questions, and then we understand the topic, right? In the same direction where the questions are going. Right? So maybe we can wait for some time, or maybe I think I can go ahead also. I'll wait for 2 or 3 more minutes and then we'll start. Okay. Right. So the first question here is, which of the following is a functionality of the control plane? So the first keyword that you notice here is control plane. So I'm just noting this down so that control plane. And here you're asking, does the control plane have to direct a data packet to an outgoing link? Or does the control plane uh, allow an individual router to create a forwarding table? Or does it help an individual router to use a forwarding table? So once again, forwarding table is another technical term, and I think data packet should be familiar for you. And computing paths, the packet will follow. Basically, computing this is basically called the routing task. Right? This is routing. So as far as question one is concerned, this is the big elephant in the room, the control plane. Right. So question 2. Which of the following messages can the open flow controller receive from the switch? So here we have another question, open flow. So you have packet in, or packet out, packet in, packet out, post status, modify state, and which are the following kind of messages does the open flow controller receive? Okay, so I'll come to the details later. So OpenFlow controller is a kind of controller, right? So it is a standardized controller. A standardized controller. Third, which of the following messages are sent by the OpenFlow controller to the switch? Once again, OpenFlow controller. So we have two questions on it. Again, it talks about the specifications and it asks which of these satisfy a particular criteria in that OpenFlow controller's function. And now, fourth question says, which of the following statements are correct? So it says central control means a single API for the network rather than an API per box. So we'll talk about this. And they also say SDN architecture decouples forwarding and control planes. So what is this SDN? This is another software defined network. Again, SDN, software defined networking. And these two are opposite sentences. Right? So one of these is true. And traditional networking architecture decouples the network control plane from the data plane. So yes, we have one more keyword here called data plane. Control plane we have already encountered. Control plane we already have. Okay. Okay, so this is basically, I think part of this is not there in the thing. So question here is, these are all statements that are made about an SDN controller, right? And which of the following of them are true? And here we have two more keywords called southbound API and northbound APIs. Hmm? And the next is, once again, OpenFlow. Which of the following statements is or true about OpenFlow messages? OpenFlow, again, there are asynchronous messages, there are symmetric messages, and which of these are true or false? And then which of the following are types of symmetric message? This is connected to the previous one. And once again, this is also a part of OpenFlow. So far, 4 questions on OpenFlow. And consider this scenario. A particular scenario has been given. And what kind of message is sent by the OpenFlow protocol? This is also OpenFlow. Okay. Another open 1, 2, 3, 4, 5. And which of the following is true about SDN deployment? So this is a general question. We should take a look at this question also. And then what are the following is incorrect about SDN? So this is once again about software defined. So 2, 3 questions on this. Right. So we've seen the questions now. So let us take a look at understanding these concepts one by one. All right. This is week 6. Yeah. So while we were looking at the questions, I was also simultaneously noting down all of these keywords. There is control plane, there is open flow, which is appearing around 5 times, and there's SDN around 3 times. And there is data plane, there is southbound API, there is northbound API. Correct. So if you have seen the lectures, correct, all the explanations are there in the lectures. Right. So since they're all in the lectures, so what I'll plan to do is to explain all of these things in simpler terms. We will try and understand these terms in a simpler language, a simple language. Okay. Now, since we've been taking this course for the past 3-4 weeks, you should be familiar with some of these concepts: routers, forwarding, routing, routers, forwarding, routing. Right. So for those of you who are not familiar, that's fine. So we are talking about something called a switch or a router. Okay, let's say a router in this case. The router is going to take some packets inside, and it is going to put out some packets. Okay, so these packets that come like this, they go out like this. Okay. But my question is there any change in these packets? If this is the packet that's going in, is this packet changed when it goes out? Is the packet changed / modified? The answer is yes. What is modified? Usually what is modified is the TTL value. We know what the TTL value is. I explained in one of the previous classes. And the source MAC is also modified. Right? And in the case of NAT, the source IP address is also modified. Right. Essentially, the router processes packets. But if you take a bigger look at this router, it contains 2 abstractions. One abstraction is called control plane. Other abstraction is called data plane. Okay. Now, what are these? These are abstractions. But this is once again using technical terms. I'll simplify this further. Right? So these are all abstractions, right? Instead of calling them abstractions, you can say we can divide a router into 2 parts. What are the 2 parts? Control plane and data plane. So when we say we divide this into 2 parts, it's not like it there is a layer, there is a clear line, there is a clear line that there is a hardware difference itself. There is a control plane on top, data plane on the bottom. So it is essentially that we are classifying some functions inside this and some functions inside this. Okay, so the control plane, and then data plane. Control plane and data. Right. So the control plane has some functions. So one example function over there is routing. Right? And one example function is forwarding. Correct. It's just an example function. So what is the difference between these two? Right? The simple difference is the routing tells the router where to forward a packet. And forwarding, it takes this instruction, takes the instruction from the control plane and performs forwarding. Okay, so this is a layman's definition of what is happening. But what happens if we go one level deeper? Right? So routing. So in routing, it takes as input neighbor topology and comes up with a plan. And according to that plan, it is going to set the forwarding tables, right? So this plan is basically the routing plan. All right. But with only this plan, it cannot do anything. It needs to implement this plan. There comes the data plane where forwarding happens. Right? It takes the plan from the routing table and fills its tables. As per this plan, if a packet A comes, send it to port 1. If a packet B comes, send it to port 2. Packet C comes, send it to port 3. Okay. D, E, port 4, like that. So you can say the forwarding is like the hands and legs of the control plane. Of the control. Just excuse me for a second. Yeah, sorry about that. So it's like the hands and legs of the control plane, the forwarding. So when such data is put into the forwarding tables, what does it do when a packet comes? It is matched and some action is taken. So there is this concept called match action. Okay, keep this in mind. Match action. So we have a match and an action. So what is matched and what action is taken? You need to keep this in context in mind because open flow is based on match action. Right. So we have a header field. Let's say the table is like this. Destination IP and then action. Okay. Destination IP and action. Let me say 192.168.2.4. 192.168.3.4. Action. Send to port 1. Send to port 2. Like that, we'll have multiple entries. These are all called entries. Right? So what you have to notice here is these entries. Who fills these entries? Entries, who fills them? It is the control plane. Who fills these entries? Control plane fills these entries. And based on what? Just the control plane fill these entries. Based on what do they fill it? Based on their knowledge of the topology. Of the topology. Right. Okay. So now we know that the control plane, okay, interacts with the data plane. By interacts, it gives information info to the data plane, based on which the data plane does something. Now coming back to this example, right? So we have a table like this, these entries. Control plane has filled these entries. Now, let's say a packet is coming. The packet source destination IP is 192.168.2.4. Let's say this packet has come to the router. In the router, what is there? This table is there. So it goes and starts checking. Do we have a match here? Yes, we have a match here. Do we have a match here? No, it does not have a match. So basically, there is just one match. So once there is a match, which is the match has happened, then we see an action. What is the action here? It takes the same packet and puts it on port 1. So switch will have multiple ports. It puts it on port 1. So essentially, this is how the internet works. It is based on matching of certain fields in the packets at the router and forwarding them onto certain ports, correct? And these ports can be varied. So just to put that into perspective, I'm going with the usual diagram. You are sitting here, and then you have a router, and then there's another router, let's say from here, 3 routers, and then another router, the router. This goes elsewhere. Finally, we have a destination, right? There are end hosts. So the destination is this. This is another end host, another server. So if you look at it from the perspective of match and action, this happens at every hop and at every node from the starting of the packet to the ending. You have a match and action here, you have a match and action here, you have a match and action here, 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 if it decides to take this path. Or if it decides to take this path, you have a match and action here, and you have a match and action here, and the action here is, let's say it's sends it over here. Then there will be a match and action here, match and action here, match and action here. And if it sends it over to the other path, it will have match and action here, match and action here, match and action. So in a way, all of these routers, they are acting independently of each other, but at the same time is able to take the packet from the source to the destination, correct? To the destination, right? Okay, so with this context, we know what is a control plane and a data plane, right? But now we are moving into the concept of SDN. SDN is software defined networking. Okay. So what is the difference in paradigm? So once again, if you want to look at the exact paper that led to the software the paradigm of software defined networking, you can go and watch the videos. But in simple terms, what is this software defined networking? It is essentially abstracting control plane and data plane, but with a small difference. So if you see, you have these routers, right? So there is a control plane, data plane. There is a control plane, data plane. There is a control plane, data plane. And there is a control plane and a data plane. But so this is the traditional route network. But what will happen if this is only a data plane? This is the data plane. This is the data plane. Data plane, right? What will happen if the control plane is put up in such a way that this control plane acts on this router also, this router also, this router also, and this router also. So this is the in simple words, this is the paradigm change that we notice in SDN. But why do this? why do we need to centralize the controller? Why do we need to centralize the controller? There are advantages. If you look at this example itself, right? Let's say that this router is getting a lot of packets. Getting a lot of packets. And these packets are forwarded based on destination IP. So if it is based on destination IP, then it will either send it over here or over here, depending upon what is there in the routing table. But what it won't do, or what it does not know, that in whether you send it this way or whether you send it this way, you will reach this part. You will reach the destination, which is somewhere over here, let's say. But what it will do, whether this link is used or not, it will keep on sending packets like this over here. In the meantime, what is happening? There are no packets here, which means this is empty. So this is a common problem in traditional networking. These machines over here, they don't have enough global knowledge. Okay, but if you abstract the control plane like this, the control plane has visibility of the network. So once there is visibility, it knows how many packets are arriving at this end, how many packets are arriving at this end. If the load here is more, then what it will do, it will send instructions to this data plane saying, you split some of the packets that are destined for this particular place to this link. It's okay because I know how to send it back to this place. So essentially the control plane, because of its higher visibility, can aid in something called load balancing. What we're talking about is load balancing. This is just one such use case. This is not the only positive aspect of having a centralized control, right? This is a centralized control. In a way, the centralized controller, what it does, it reacts to network events. What is the event here? Congestion or link saturation, right? So when we abstract the control plane to such a centralized place, then we have certain advantages. So this is what we're going to talk about. And now the question arises, how does the control plane communicate with the data plane? So how does the control plane communicate with the data plane? Because you see, the control plane is not on the device, it is off the device. This is also off the device, off the device, off the device. So there should be some mechanism to communicate, right? Some mechanism. Let us say this is a Cisco switch. This is a HP switch, sorry, HP router. And this is a Juniper. I'm only taking these names for example, right? This is just and this is on another company XYZ. Okay. So the control plane should be able to communicate with all of these devices. So how does that happen? In spite of device heterogeneity, control plane data plane communication should be seamless. So what will happen if at the control plane I have to write 4 types of codes for 4 different companies? Okay. Code 1, code 2, code 3, code 4. All these codes do the same thing. That is, they push some information. But just to communicate with this switch, you're writing a particular type of code. To communicate with this switch, you're writing another type of code. And to communicate with this switch, you're a switch. Okay, when I say switch, don't get confused. I use the word switch and router uh, the same the same meaning, right? So you can assume that when I say switch, I mean router, or when I say router, I mean switch. And this code 4 is communicating with this node, right? So I mean this code 4. So instead of writing all these different types of code, is there a way to communicate with all of these switches using just one type of code? The answer is yes. What is that? That is called the open flow protocol. So the open flow protocol is basically nothing but it is a standard that is followed by all these switches, all the routers, most of the routers of the high capacity routers. So it is nothing but a standard that is followed by most of the high capacity routers. Okay. But how does it happen? So all these manufacturers, they have an open flow agent that is running on these switches. So this open flow agent will be able to understand the messages that are coming from the control plane, which has the open flow specification. Now this will become more clear as we move forward. So now we have seen traditional networking, and then we see how we saw match and action, and how the whole world of networking works on match and action only in a lot of ways. That's what takes your packets from point A to point B. And then we came into understand what is the control plane and data plane, right? So this is the control plane and data plane. Is it the control plane and data plane? And then we spoke about SDN and a centralized controller. And what is a problem with a centralized controller? Problem is it needs to be able to communicate with multiple different types of devices from multiple manufacturers. So someone had to bring a common standardized mechanism for control plane data plane communication. And that is what OpenFlow is. Right? So now if we go back to the initial list, right? We've understood what this is. We've understood in the sense we've covered the motivation for what this is. We've seen what this is, seen what this is, we've seen what this is. So southbound, northbound API, we will talk about it in the context of the particular question that we will answer. one of the origins of STN, right? So now I'll just briefly talk about what was said in the lecture. So STN, right? It came from something called the Clean Slate Project. So what was the motivation for this project? The internet was started with a very small scale, but nobody envisioned that it will go this big. But the moment it went big, when it started encompassing a lot of people, it started going out to the common man, right, to everyday world. The initial idea of the internet, initial mechanisms that drove the internet is not sufficient. So someone thought, let us stop everything and let's design internet from the bottom up, right? So this was done by someone called Nick McKeown, and the idea was that the internet is broken. Right? Internet is broken. Is broken, and they tried to fix it. And from this came SDN. Okay. Hmm. Then essentially traditional networking, software defined networking. We know what the difference is. So there is a controller, right? There is a controller here. Right. So basically, in traditional networking, both the control plane and the data plane reside on the device. But here, only the data plane resides on the device. Right? And then we see that the data plane's major aspect is to forward these packets in the fastest possible manner. Right. So in this paradigm, right, the data plane operates in the order of nanoseconds. But since the control plane involves CPU in the sense any sort of processor that is general purpose, it tends to do things in the order of milliseconds. And what are all its possible functions? Routing is what we saw, correct? And management also. Right. Okay. So with this context, right? With this context, I'll skip over the example and we'll move on to OpenFlow, right? But I think I should give you more context on control plane and data plane. So before we go into OpenFlow, we'll just take a look at the key diagram that defines it. Okay. Let's start from here. So you have these switches, right? Or routers, you can say. So this is the data plane, and the above is the control plane. Okay. The above is the control plane. So what is there in the control plane? There is something called the controller. Correct. So this controller has a network operating system. NOS, they call this NOS. And on top of this network operating system, we have multiple applications. App 1, App 2, App 3. And let's say this first app is for routing. The second app is maybe a firewall, etc. So this is the controller. Okay. So now this controller, in order to communicate with the switches, right? It needs to communicate here. It has its own connection. So what is it that it sends to the switches? They're called flow rules. These flow rules are nothing but entries in the forwarding tables. That's all. The rules, it might be a bit confusing. These are nothing but entries in the forwarding table. So right. So the API. So maybe I should explain what API also is, right? APIs, programming interfaces. So an API is nothing but an abstracted set of code that can be used by a system. So let us say I am writing code. So what is an API? So I have written some code. Okay, and this code has an input and an output. Now, this code, right? This code can also be called as an API because for some particular input, it is giving another particular output. So there are some APIs here. There are some APIs here. And these APIs help the network operating system to send flow rules, to send instructions to these routers. These are all called southbound. Southbound APIs. So for the same NOS to communicate with the app, we have northbound APIs. right? So this tends to give some level of introduction to all the keywords that we gathered from the questions. So without details of abstraction and all the other aspects, so if we want to summarize this southbound and northbound, we have controller, these are all the switches, and these are all the applications. So we have northbound API, have southbound API. Okay. So this is how it is. This is the data plane. This is the control plane. Okay. Now, finally, let's go into OpenFlow. So I hope all this context is understood by the time we come to OpenFlow. Now, as we said, OpenFlow is a way for the controller to communicate with the network devices. Which are all the network devices? These are the network devices, right? So controller communicates with the network devices using OpenFlow. All right. So what did we call this communication aspect? It is the southbound interface, correct? So an OpenFlow protocol is basically a southbound API. Okay. And the communication happens in multiple ways, right? So I'm just writing some points here. So it operates between controller, is the network operating system, and the switch. Okay. There are three types of OpenFlow messages. Right. First type is controller to switch. The second one is asynchronous. Which is switch to controller. The third is symmetric messages. So essentially, these are all the types of messages that people can use to enable communication between the switch and the controller using the OpenFlow protocol. Right. So let us see which are all the controller to switch messages first. So when it comes to controller to switch messages, we have something called features. And then we have configure. Features, we have configure. Modify state, and we have back it up. Okay, now we'll see what each of these types of messages are. So once again, on the first look at OpenFlow, it will be confusing. But if you forget about the complexity and just understand, this is just defined by people who created this OpenFlow protocol, that these are all the different types of messages a controller can send to the switch. Okay, just to give you context, this is the controller, and these are all the switches, right? Okay. This controller is running OpenFlow, and all of these switches also support OpenFlow. Because for a protocol to work, you need both the ends to understand the same language. The language here is OpenFlow language. Right? So the first type of messages, features. So essentially, when a switch starts communicating with the controller, or rather, when the switch comes into existence and the controller wants to understand the switch capabilities, it sends a feature request where the switch sends back all the features that it has, or what are all its capabilities and what are all its specifications. So who initiates this? The controller initiates this. Initiates this process. Right. Second is configure. If you want to configure certain options in the controller, sorry, in the switch, then also the controller initiates it. These are all configuration messages. And if the controller wants to, let us say, add, delete, or modify flow entries, right? This is important. Add, delete, or modify flow entries. Correct? So where do these things happen? It happens in the forwarding table. And the other name given to this forwarding table is the open flow table. That's all. They say open flow table, but it is nothing but the forwarding table. Keep it like that. But in the context of examinations, you have to write open flow table only. When you're talking about open flow, you have to talk about it as open flow tables. And finally, the packet out, correct? Packet out. So a packet out is a response to a message called packet in. That's all. Packet in is sent from the switches to the controller. We'll look at that. So from the controller to the switch, you have these four kinds of messages. Right? And what are all the switch to controller messages of second? Switch to controller messages, right? What are all these? They are packet in. I just said told you, right? Packet out is a response to packet in. To packet in. So packet in is nothing but, okay, we'll come to that later. If I say this now, it will be a bit confusing. And then there is also another message called flow removed. And there's one more called port status. Right. So if you look at flow removed, whenever a flow table entry is deleted, when I say entry, I'm talking about these entries. This is entry one, entry two. When if you delete one of these entries, right, then it sends in its response that the particular flow has been removed. Similarly, if you change the status of a port, if a port goes down or up, whether it is functioning or not functioning, if that status changes, the switch has to inform it to the controller so that the action should not say forwarded to that particular port which has gone down. And finally, packet in is when a packet is arriving at a switch, and this packet has a particular destination IP address. But in the flow table, there is no match, meaning the switch does not know what to do with the packet. So what does it do? It makes a copy of the packet and sends it to the controller as a packet in message. And so the response to this packet in message is packet out. And so these are the three different types of messages that happen from the switch to the controller. And right, and if you see the intro video, all of these messages are explained, and there is a summary table as well. For further details, you can take a look at that. So I'm just reading it out from there. You have feature request, you have features reply, and you have port status, you have packet in, you have packet out, you have flow modification and flow expired. Right. So what we did not talk about is modify state. This modify state, essentially what it does is it adds, deletes, or modifies flow entries. So again, what are flow entries? Flow entries are the ones that you saw here. Okay, so these flow entries are the ones that we saw here. You can either add these flow entries, delete these flow entries, or modify these flow entries sitting from the controller. So the controller has the power to do that. How does it do that? By sending these modify state. Okay. Right. So now I think with this context, we can definitely go to the questions. Pasting some messages. Okay. Right. I'm just playing the questions here. I guess you can see question number 1. Just hold on. It's in okay. Just wait for all the questions to load. Right. So all the questions are here. So let's solve these questions one by one. So which of the following is slash are a functionality of the control plane? So we know what a control plane is. It's not a mystery anymore for us. And what does the control plane usually do? Okay, let us see. A, directing a data packet to an outgoing link. So it says it'll take a data packet and putting it on the outgoing link. So who does that? The router does that. Of course, the router does that. But which part of the router does that? It is done by the data plane. Data packet is nothing but a packet. That's all. So this is a data plane operation. This is not correct. This is not a functionality of the control plane. Next, individual router creating a forwarding table. So what they mean by this is creating a forwarding table. By creating a forwarding table, what is it? You need to fill the forwarding table with entries. What is the meaning of creation? Creation means you create a table and you fill it with entries, correct? Who does this? Who fills the entries? The control plane does it. We just saw it, right? Control plane. So this is correct. Meaning this is a functionality of the control plane. And then C, individual router using a forwarding table. So using a forwarding table, that's the key here. So how do you use the forwarding table? You take a packet, you match it, and then you perform an action. It's basically forwarding. Correct? This is done by the data plane. So this is not correct. This is not a functionality of the control plane. And finally, computing paths the packet will follow. So what this means is you compute the routing data, correct? So you have the details of the global uh, the topology based on which you bring the routing plan. I mean, when I meant plan, what I said before, it meant that it is basically the routing functionality. This is also done by the control plane, correct? Control plane does the routing. This is basically nothing but routing. So B and D are correct. So question number 2: which of the following messages does the OpenFlow controller receive from the switch? So we're talking about controller, right? Controller, and there are switches down there. We just were seeing. So these connections are bidirectional. So which of the following message does the OpenFlow controller receive from the switch? Packet out. So what is packet out? Packet out is from the controller to the switch. Right? So this is not packet in. Packet in is from the switch to the controller. So when does packet in happen? Packet in happens when the switch is not able to understand what to do, when the entry is not there in the OpenFlow table. So it sends a copy of the packet to the controller, and that is called a packet into the controller. So it's always with respect to the controller. Packet is in, packet is out. In, out. In means coming from the switch to the router, sorry, to the controller, and the out means going from the controller to the switch. So packet in, yes. Port status. So we were just seeing in the previous case, right? So port status is also sent from the switch. We saw these 3 types of things, right? And modify state. Modify state happens from the controller to the switch. It tries to modify the state of the switch. By modify state, it means that you can update the flow table by either adding rules or add rules, delete, or modify existing entries. Correct? So the answer is B and C. Okay. So once again, this is also a similar question. Which of the following messages are sent with OpenFlow controller to the switch? Now they're asking the opposite. Controller to the switch. Which of the following? Configure? Yes. Configure because the controller wants to configure the switches. Controller configures the switches. Right. So this is we just saw in the theory part of this session, right? But this is the control configure messages sent from the controller to the switches. And what about port status? Right? Port status we are given true here because it's going from bottom to top. So this is not flow removed. So who says that flow is removed? The switch says the flow is removed, correct? The switch says this. And to who is it informing? It is informing to the controller that this flow is removed. So this is also not the answer. And modify state, we are given false here. Now it's true here because it's the opposite direction. Modify state is the same thing. Add, delete, or modify. Okay. Now, next question. Okay. So which of the statements are correct? Okay. So central control means a single API for the network rather than an API per box. So this is essentially what we discussed. You remember I drew a diagram where you had code 1, code 2, code 3, code 4, because there are 4 different switches from different vendors, vendor 1, vendor 2, vendor 3, vendor 4, vendor meaning different companies. And to communicate with each of them, they need their own specific code, or rather their own specific APIs. What happens? This becomes API per box. So this box, they call this a box. This is API 1, API 2, API 3, API 4. So these are all per box. But in the context of a central control, you replace all of this, by a single API. And that API probably in this case is OpenFlow. Correct. OpenFlow. So this will be able to communicate with all of the different boxes, types of boxes. So yes, the answer is correct. Second, SDN architecture decouples forwarding and control planes. Right? SDN architecture separates control planes and forwarding is nothing but data plane. So this is correct. See, SDN architecture couples forwarding and control planes. This is wrong. This is basically the opposite of this particular statement. And it doesn't couple it, it decouples. That's the whole point of it, right? So this is wrong. And traditional networking architecture decouples network control plane from the data plane. So we're talking about traditional networking architecture. It does not decouple because control plane and data plane are all part of the same router. It's on the device, right? So it decouples it. So it does not decouple it. In fact, it couples it. Right? If they say couple, then this statement is correct. But now it is wrong. So the answer for 4 is A and B. Right? So let's look at this question now. So consider the following statements about the SDN controller. By this time, controller should be clear, and then determine which of the following statements are true. Okay, we're talking about the SDN controller. So, moment we say controller, we go to the top. The first statement is southbound APIs are those which relay information between the controller and the individual network switches. So you remember we had this diagram. Controller, applications, correct, and switches, right? So what did we have here? We had the southbound, and this was northbound. This is northbound API. This is southbound API. So with this diagram in mind, let us take a look at this. The southbound APIs are those which relay information between the controller. Where is the controller? The controller is here. Okay. And the individual network switches. So this communication. Correct? So these APIs enable communication between the south part of it. When they say south, based on this diagram, this is bottom, right? Bottom is south. So this is the communication that is enabled with the help of southbound APIs. So statement P is correct. Okay, let's mark it. Let's mark it as true. Now let us look at statement Q. Northbound APIs are those which relay information between the controller and the network control applications, right? As per the diagram, these are all the network control applications. NCAs, network control application. These are all applications basically. So the controller uses northbound APIs for this communication. Right. This is also true. So P and Q are true. Then let us see the last one, even though right now it's not required because this is the answer. We know this. This is only possibility. Statement 3 is southbound APIs are those which relay information between the controller and the network control applications. Meaning between the controller and the network control applications. Who does that? Northbound API. Who up this said southbound API? So this is false. Right. So the answer is C. Okay. Now moving on to the next question. Which of the following statements are either true or false? Okay. False about the open flow messages. So we saw, right, asynchronous messages, synchronous messages. Let me go to that part. Right. So asynchronous messages are what? Asynchronous messages are switch to controller. Right. Okay. So which of the following statements are false? Asynchronous messages are sent from the switch to the controller. So this is true. Asynchronous messages are sent from the controller to the switch. This is false. This is the converse of this. Correct. So symmetric messages can be sent both from the controller and the switches. Right? Yes. This is also true. I mean, I think we didn't go deep into the symmetric messages, but symmetric messages meaning these messages can be sent both ways. You can either start from the switch or from the controller also. And symmetric messages are usually used for diagnostic purposes between controller and switches. Yes, so basically that's the function of symmetric messages. Right. If you go and look into the table that was shown in the lecture, you'll see what all the symmetric messages. But for now, we know that this is the only false statement. So the answer is B. Right. So this is the answer for question number 6. Now let's move on to question number 7, where they're asking. So it's basically a continuation of the previous question. Right? Now they're asking which of the following are types of a symmetric message. Now the answer to this is directly from the table that was taught in the class. So the answer here is A. A is a hello message which can be started either from the control by the controller, open flow controller, or the switches, and echo. So these are the two messages that you can try. When there are symmetric messages. Set config and packet in. We already saw this. Set config is something that is done from the controller to the switches. They're setting some configuration, and packet in goes from the switch to the controller. Correct. This is from switch to controller. This is controller to switch. So the answer is hello and echo. Right. Now let's move on to question number 8. So here they're giving us a scenario. And what is the scenario? Consider the following scenario. Let's draw it. Packet arrives at a switch S and does not match any entry and does not match a flow entry in any of the flow tables. So there are flow tables here, right? FT1, FT2, there are multiple flow tables. So this packet comes and it tries to match here, P, P. It is not matching anywhere. So once, I mean, we spoke about this previously also, right? So once an open flow switch does not find a match, what it does, it creates a copy of it and it sends it to the controller. And because the packet is going to the controller, what is it called as? It is called as packet in. The answer is packet in. Because hello is a symmetric message, we will go from either direction. Flow modification is from controller to the switch. Port status is from the switch to the controller. Sorry. Switch to the controller, right? So it must be familiar at this point of time. Right. Okay. And moving on to question number 9. Which of the following is true about SDN deployment? Okay. An SDN-enabled networking device or devices can coexist with traditional networking devices. So basically what they're saying is there are two types of devices. What is the first one, traditional, and SDN enabled, advanced. So when they say SDN enabled, what they essentially mean is open flow enabled. That is, the switch will be able to understand open flow protocol. So now, when you are looking at traditional devices and SDN enabled devices, can these two coexist with each other? That is the answer. The answer is yes. Just because it has an extra capability does not mean it has lost its primitive capabilities, which is basic forwarding and right. So it can communicate with traditional devices also. So first one is true. Second, SDN enabled networking devices cannot coexist. So this is a converse. So this is not true. And third is traditional networking devices cannot be transformed to SDN through firmware/hardware upgrade. So this is a bit of a dubious statement. So when you say firmware upgrade or hardware upgrade, so some switches may need a hardware upgrade, some devices need a firmware upgrade, but in the context of this SDN, uh, it is assumed that yes, you can upgrade traditional network devices, but you have to bring out a new iteration of these traditional network devices, right? So this is also false. And then finally, SDN enabled end hosts do not need ARP or reverse ARP. So this is going somewhere else. So basically, address resolution protocol, right? So basically, who it sends, it basically finds out as in a the local area networking environment. So an ARP message tries to find out who has this particular IP. Please let me know. It's basically the address resolution, right? So I mean, who has the particular address, MAC address. So in this case, it is not, SDN does not mean you let go of these capabilities also. So this is also false. They need ARP still, right, in order to find out their uh, surroundings. So next is, which of the following is incorrect about SDN? So SDN is about decoupling the network control plane from the network data plane. Which of the following is incorrect about SDN? SDN is about decoupling the network control plane from the network data plane. Yes. So this is true. They're talking about which is false. We've seen this multiple times, right? You're decoupling the control plane from the data plane. And B is SDN is about providing logically centralized control over the data plane. Yes. In fact, that's what we did, right? We took the control plane and then we the control plane we place the controller. This controller is communicating with all of these devices in the bottom, correct? And the third is SDN enabled end hosts can take advantage of SDN controller to do the routing. So SDN enabled end hosts can take advantage of SDN controller to do the routing. So basically end hosts have nothing to do with the controller. End hosts would mean your computer, my computer. We're only talking about networking devices. So this statement is false. When will the statement become true? They say SDN enabled networking devices, right? In that case, the statement will become true, but it is false. This is false. So the next one is SDN is to remotely control and configure the forwarding behavior of the networking devices. So this is also true because the controller is sitting somewhere and we can configure the forwarding behavior of the networking devices from a remote place, from a remote location, right? So yes, that is also true. It is also true, and essentially we end up only with one option, which is C, which is the answer. That is what is incorrect. And of course, I think for this, A is the answer, right? So what we did today was we learned about match and action, and then we transitioned to SDN, and then in SDN we learned that the control plane and data plane are separated, and the control plane is centralized. And then finally, we came to a particular instance of a centralized controller called open flow protocol. Correct. So these are all things that that we saw today in a very in very using very common language, right? So and then we answer some questions also. So I think this would be the conclusion of the session today. So what possibly okay, and then I think since we have some more time left, I can give an introduction to what can expect in the coming weeks. Right. So now we are talking about centralized controller, and its communication with switches, right? So we are still assuming that the data plane, correct? The data plane is dumb in the sense that the data plane is only forwarding, it's matching and forwarding, correct? So the next advancement, or rather the next direction is, what if the data plane is given some intelligence? What if the data plane is given some intelligence, right? So in a way, the same way how you can program the controller, you can also program the data plane. And that is what is called as programmable data planes. Okay, and these programmable data planes are nothing but programmable network devices. These are all nothing but programmable network devices. That's all. So basically, you write your own logic and push it to the data plane. But why? Why do we do that? Do we need this? Why do we need this? The reason why we need this is, in spite of having a centralized controller and possibly abstracting some logic, and possibly performing some logic, some operations here, right? You are able to send back the results, and the switch will take an appropriate action. But all the processing happens here, all the logic, correct? It happens at the controller. The problem here is the data plane happens in nanoseconds, but the controller works in milliseconds, right? So in terms of forwarding decisions, right, if you have a bottleneck like this, that the data has to go here and then I get the response back here, this is not ideal because you'll have a bigger queue here, or you won't get the decision fast enough where you have to drop some packets. So if you can take a part of this logic, right, take a part of this logic and put it into the data plane, maybe then uh, we can save some time in terms of processing. But what that means is, for not for all the packets, I will go to the controller. For only for some packets, you take this controller path, which is called the slow path. But for most of the packets, I will use the logic that is inside this box, inside the data plane, and I will forward the packet based on that logic. Right? So this is where the concept of programmable network devices or programmable data planes came from. So what are all the kinds of devices here that you can program? You can program switches. You can also program smart NICs, right? So you can program switches, you can program smart NICs and the like, right? So NICs, these are all network interface cards. This is where you plug in your Ethernet cable. So what if you make them smart? What if you put some logic into it? These are all programmable data planes. Right, I think this is what probably we'll be looking into the next week. And we'll conclude today's session. And if you have any questions, you can ask me. I'll be here till 8 o'clock. Right? Thank you. Thank you, Neetu. Thank you. If you have any questions, you can let me know, right? Okay, sure. Oh yeah, okay. I'm happy you find it useful, Neetu. Yeah, thank you for your feedback. Yeah, the idea um, is to not repeat what was said in the class. We try not to do that, but to try and explain it to people who possibly need some more explanation to understand the concepts. And we do that in the context of the questions that we have to solve. Yeah, I mean, if you have any suggestions, also you can give via the feedback form, or yeah, you're free to talk. You're free to let me know if you have to change. If I have to change something or anything else. All right. So anyway, thank you. Thanks a lot for your feedback. Thanks.